over the link. And then we have again back to electrical signal. So we have received signal, and then we look at zeros and ones again. So there are some things we need to learn, what we are going to look into during the lecture. So first thing I wanted to talk to you about, I think we have not covered that there is these eye diagrams. So here is a short picture on what we need to see, just understand how the eyes looked. So on top you have so there's a recovered clock signal from the pulses. So have a one so here is 1 bit, there's next, there's one more, then like here we have up to 12 bits showed. So what we do that if we overlay 1, 4, 7, and 10, we get something like this. If we overlay all of them, then we get something like this. So and it's called an eye diagram because then you kind of this part is called an eye opening, and there can be different representations. You can have like here you show two eyes, so one eye is partially showed, but then one eye is center in the middle. Sometimes people show 4, 6 multiple eyes because depending how you overlay there, you can also see impact of different uh, patterns which you use for testing, and these are pseudo-random bit sequences, PRBS, and depending on the sequence, then you can see what transitions exists and what combinations of zeros and one exists in a data stream. I just wanted to check, is everybody hearing the sound? Since nobody is complaining, maybe I have sound on my side. So just if you can tell me if the sound is fine.
Yeah, I think the sound is fine.
Yes.
Okay, good.
Yes.
So sorry, I have to check it maybe in the beginning. Right. So and then what happens here is that why we call it an eye. It's also that when you have more impairment, that you have this. This is what one could call an opened eye, and then the eye is starting to get smaller, and there's no eye opening. And what you could see that. There's some other things here, but yeah, I'm not covering this later today. But I mean, these two parts also could be used to detect, and it's part of like dual binary signaling when they use these eyes instead of this eye to process the signals. So we are in this lecture we are going to focus on two-level signals, which is PAM2 or on-off king, and PAM4, and let's see higher order as well. So therefore I have these graphs. So here is again representation. It's just visualization in this case. So it's really like just visualization, and then on the right side, this one here is an eye diagram from a paper. We measured this eye diagram in the lab back in 2017. So I just wanted to show that yeah, I mean we could plot an ideal eye diagram, but in experiments we have a different other impairments, and eventually this might look like an eye diagram which is the performance is still good enough to correct errors by using forward error correction codes. So and also I showed that you can have also these pulse amplitude modulation signals. In this case, 4 means that there's 1, 2, 3, 4 levels, and this one can be called on-off king from optics, or in electrical community it can be also called pulse amplitude modulation with 2 levels. So and then you can have 6, 8, 16, and but that also has limitations because if you divide this eye diagram, for example, this one into more levels, then the eye opening will be even smaller because the usual problem is that you gain something and you lose something. In this case, when you go from 2 levels to 4 levels, then you see that for each level here you have 1 bit here, so it's 1 bit per symbol. But here you can have 2 bits per symbol. So by using PAM4, one can obtain twice the bit rate by using the same symbol rate. So yeah, so in PAM4 we have symbols with 4 different levels. In PAM2 we have symbols with 2 different levels. So by using the same symbol speed, which is also related to the bandwidth of the system, then we can transmit double the information within the same bandwidth of the system. Right. So that all seems to be a very, very good thing, because then we can transmit twice as information by using same optoelectronics. But there should be something, a price to pay, and something bad with the system. And that is that we have uh, so if we have the system, then the dynamic range, so from 0 to 1, it will be the same. And then, I mean, if we have a system where which we can operate in 2 levels, we will definitely use the whole dynamic range of a system. So, and then if this dynamic range is used for 2 levels, and then if we put 2 more levels in, then this eye opening here, it gets, you need to divide the eye opening by 3. So now we have 3 smaller eyes, and that has impact. I think you have done already some simulations in practical works, I hope, where you have to look in these, yeah, and how the bit rate looks for these kind of curves. So the thing is that the eye opening decreases by 3. So you need more signal to noise ratio for PAM4 to get to the same bit rate. But and that we're gonna discuss later, and that's always a trade-off in a system. Are you limited by noise or linearity? And yeah, so this is and you try to optimize, because for some systems, if you want to go higher speed in symbol rate, then PAM4 might not be feasible because it lacks signal to noise ratio. Right, but then if we look again at what I talked about, the bandwidth. If we compare, this is without pulse shaping. So we have an electrical spectrum, and we have, if we look at the Nyquist frequency for both of these PAM4 and NRZ signals. So this is so when I was talking about getting twice the speed, then I was talking that they're utilizing the same bandwidth. But if we compare these modulation formats not at the same symbol rate, so these signals do not have the same bandwidth. So these signals are at 56 gigabits per second. So with PAM4, we only require half of the bandwidth, which is 14 gigahertz. And for non-return to zero, we need to go to 28 gigahertz. So if just calculate the Nyquist frequency, of course, this is within the assumption that the channel is a flat, so ideal channel. So then there's then there's no significant digital signal processing involved. So just to compare, if you want to achieve the same bit rate, then you get you can do it with smaller bandwidth. But again, we should not forget that the signal to noise ratio still gives there's more pulse amplitude modulation levels give problem there. So yeah, I think I have one example which I will prepare and send it over after this lecture. There's some MATLAB code which you can run and compare these bit rate and symbol rate, and what is the bit rate tolerance and penalty. Yeah, for these systems. Right. So, and why people started to look into these PAM4 modulation format? Because on the left side we have channel response of RF cable, and then if the cable gets longer and if you go to higher frequency, then your frequency response starts to drop. So you don't have ideal flat frequency response, but you have a bandwidth limited system. And for bandwidth limited systems, that's one of the ways how you can increase the bit rate you're transmitting. So yeah, so that's why industry has been looking into this in and not only on of King or PAM4, PAM2, but in PAM4 and recently PAM6, PAM8, and it's a big optimization problem which modulation format will be next for these intensity modulation direct detection systems to enable, for example, 400 gigabit net rate systems on a single wavelength in O band, for example. Right. Then I have some examples here more that you can see. These have a different shape. We're gonna talk a little bit about the pulse shape later on in the lecture. I just wanted to show a bit of comparison. This is again, we have a PAM2 eye diagram, wide open, and then this eye diagram. Then if you look at separate bits, it looks like this. If we look at PAM4 eye diagram, it looks like this with all the transitions, and then we can see all these transitions. This transition here also is somewhere here, and this one here. So you get these three transitions, so you kind of get like this here, like this line here. And then if you look what I was talking about these how many symbols, so how many bits per symbol. So we have two levels, one information bit in every symbol. Here we have four amplitude levels and two information bits in every symbol. So at the same the symbol rate or baud rate, you can get higher speed, but then the signal to noise ratio here due to in each eye it's lower signal to noise ratio. So and therefore more it's more yeah, so more sensitive or like it's bigger impact from the noise in the system. Right. So then there's also other things that is here represented, that the noise margin is decreasing when you increase the speed. So here if you look at PAM2 or PAM3, or this can also be regarded as electrical low binary, depends on coding how do you look. So here your noise margin is 0.5 and here 0.33 if we compare from PAM2 to PAM4. So that's what I was talking about, that yeah, so here the eye opening is much smaller. Right. Then I wanted to also talk about little bit about different ways how you can assign symbols. So how you can assign bits to the symbols. And in case of here I have an example of comparing if we go from non-return to zero to PAM4, and then in PAM4 to each symbol, like symbol is here, symbol 1, 2, 3, 4 symbols. So these are four symbols. So we have symbol 0, which is at the lowest level. So then there's a couple of options how one can assign in binary code. Then you assign 0, 0, 0, 1, 1, 0, 1, 1. And then if you do a bit more if you put a bit of thought into this by just not putting by choosing to change how you put it in, it called a gray coding, And why it's called the gray coding? Because if you do this, then if you look carefully, so these are symbols which are quite close to each other, and if you see that there's a difference here, because then for example in this case, this symbol, this bit is the same, this bit is the same, and this bit is the same. So when you have an error in one of these symbols, then in gray coding, it will translate only to one bit error. But in binary coding, here you, for example, have this bit is the same, but here you don't have that. So then if you have error on this symbol or on this symbol, then it will lead to 2-bit errors. So and half of the symbols, so your bit error rate compared to symbol error rate without gray coding will be worse, and as we see here, potentially even 50%. So yeah, so that's why when you do this more advanced signal processing, you also have some freedom, and you can find clever ways how to minimize errors here. All right, so I think this is important to know. And then there's also how do you generate these PAM4 signals? So in this case, I wanted to share the way how it was done. Uh, I mean, there are a couple of ways how you can do it. One of the ways when you have a when you can use a bit pattern generator, when you have two non-return to zero streams, and then you can what's happening here. So these are quite similar here graphs, and yeah. So here they define what that is most significant bit and least significant bit pattern. So these just and then what you want to do is that you want to least significant bit, which is here, you want to attenuate this. So what you're, I will show this, I will show in the next figure how it looks in when you visualize it. So you need to attenuate this least significant bit. Of course, these two patterns needs to be synchronized, and then you can so synchronized on a symbol level. So these symbols going through here and through here, they need to have the same timing instance, so you can combine them here. So in RF power divider combiner. So yeah, so this is the way when I started do experiments on pulse amplitude modulation. This is how we were generating PAM4 signals. So what I mean, the I will just go back and forth. So so this is what you do with the most significant bit. You have the same amplitude, and then with least significant bit, if you reduce it by 6 decibels in electrical domain, then your amplitude is gonna reduce by half, and here you can see it. For the orange least significant bit in this example, we go from 200 to minus 200 millivolts peak to peak. And for the most significant bit, then you get from minus 400 to plus 400 millivolts peak to peak. And as I mentioned, they need to be time synchronized. So where you have a transition on least significant bit, then you need to have a transition on most significant bit. And there's also in these kind of systems, yeah, so there needs to be a delay to align the start and end of the symbol, but then you can actually shift one of the stream more and less the other, and depending on that, the bit to symbol mapping will change, and then yeah, so yeah, but I'm probably going too deep into this. But the thing is that you need to have at least 3 elements in electrical domain to do this. If you want to do it at very high speed, then the problem is that you need to have connection here, and if these are separate components and you use RF cables in between, then you will have RF loss, and at very high speeds, this is not preferable option how to generate PAM4. My group stopped to use this method around when we achieved 100 gigabaud PAM4. Then we understood that with this method, if we do it in the lab like this, we're not gonna be able to achieve 200 gigabaud PAM4, so twice the symbol rate speed. Right. So then the other thing is how do you receive these PAM4 signals? So here's just an example how you would do it. So then you kind of need to use a PAM decoder. So you need to decode into separate non-return to zero and most significant bit and least significant bit streams, and then you can count individual these two patterns. You can count separately. So this is how would you, if you wouldn't use any digital signal processing but just a test and measurement equipment, then you need this is how you would do. And then yeah, so you need to decide so you need to have a clock signal. So you need to know where the bit starts, where the symbol starts and symbol ends. And then you can say, okay, 0, 1, 2, and 3. So these are 4 symbols I have here, because if you put some different thresholds, this is how it was done with the typical error analyzer together with the bit pattern generator. And these two instruments were like a backbone of all communication research up to maybe 40 gigabit systems. Now I think the highest is 128 gigabit system, which is available for test and measurement. And this method is still very good because in this way you can do tests very quickly. So you can test multiple components in a short time, so you can perform very quick tests. So this is still for industrial research. This is very valuable tool to use it. So right. Then if we talk a little bit about the detection, here is you need to set up these 3 thresholds, and the threshold on the highest eye, on the middle eye, and on the lower eye. And then actually yeah, so then you kind of then you kind of assign what is the level, and then you decide, okay, this is what, then you can get back to the gray code again, depending on a threshold, and there's some decisions you need to make. For example, for middle, is it 2 or 3 or it's 0 or 1? That's a threshold. You can decide, okay, it's there or there, and then you have one more threshold, and then you say, okay, is it 0, 1, 2, or 3? So then you can decide whether it's here or below here. And then again, so with middle you can do in maybe in a first step, and then you decide, okay, if it's 0 or 1, then you decide here, and then you have a next threshold to decide whether it's here or here. So yeah, that's the way how to do it. Right. Then there's also some eye diagrams of test and measurement equipments. So on the left and on the right, we get different shapes of signals that we're gonna talk about later on. I mean, one potential thing what can happen there is that if we go with the higher speed as it is here, it's 120 gigabaud PAM4 signal, and then which means that it's 240 gigabit per second speed here. So it's an electrical signal, and you see the three eye openings. Then these transitions they become not so sharp up, but they're more it takes longer time to do. Then this eye opening in this direction decreases, also decreases in this direction, because this direction is because you have a limited bandwidth, and then of course you can also do some signal processing here, also to do pulse shaping. So I'm not actually aware what type of pulse shape is used. I don't assume that it's the same here or here. So we're gonna talk about the pulse shape slightly later in the lecture. So and this one is, for example, for 64 gigabaud PAM4 signal. This is very clean signal with very nice transitions. And here there's no specific pulse shape used. I mean, you don't use root Cassane pulse shaping here, so this is how you get well, yeah, so you don't do a specific more pulse shaping. So these actually transitions are defined by the design of an instrument. Of course, nowadays you can also, in pulse pattern generators, you can do a bit of signal processing to shape these signals cleaner, right? Okay, so then there's another instrument which could be used to generate pulse amplitude modulation signals, not with using this pulse pattern generator, where we combine two streams, we delay one and we attenuate other one, and then we sum it. Here I'm talking about arbitrary waveform generator called AWG. So with that one can generate arbitrary waveform. So you can basically generate even a sine wave with it. Depends on which frequency you want to do it. So here I just want to show this is a state-of-the-art instrument here in a blue line. That's a bandwidth or a channel response of a signal. So as you see, it's not flat. So it has a decay after 70 gigahertz. And it has been measured for this 20 dB bandwidth up to 100 gigahertz. But there's a big improvement from gray curve to the blue curve. I'm also going to show how fast signals one can generate with this version of instrument and this version of instrument using digital signal processing. Here, I think it will be in some in the next lecture or in following one. But I just wanted to show you some examples what could be done with these type of instruments. And these eye diagrams are from the instrument with a blue curve. So it's most likely using a short piece of cable to oscilloscope, and then there being used some signal processing like pre-equalization. I'm going to talk slightly later in the lecture about pre-equalization, post-equalization, and also a little about signal processing, what's being done on pulse amplitude modulation signals. So on top left, which is this one, then we have a 112 gigabaud signal, which is 224 gigabits. Then on top right, then this symbol rate is increased from 112 gigabaud to 160 gigabaud. And then this increased even more on this graph, which is 200 gigabaud for 400 gigabit net rate. So what you can see here that the signal, the shape of signal from this eye diagram to this eye diagram is significantly different. So because for this higher symbol rate, you still have the same bandwidth, So what happens when you decrease the bandwidth, then the eye opening in this direction decreases, and also it decreases in this direction. So bit error rate for this signal and this signal is very different. So the implementation penalty, or if you measure, yeah, I mean the bit rate. So this one is most likely in observation period when you measure maybe in 5 minutes might be error free. This one, it's hard to say. Can be error free, but can also be that it has some errors which can be corrected with further error correction limits. And then, so just to compare at the same symbol rate, if we look at PAM4 and PAM2 or non-return to zero signal or on-off king, so there are different names for two-level signals depending how you look at it and in which field it's used. But what you can see is that if we compare PAM4 and on-off king, then this one will have a lower, so this one will have higher bit error rate than this one. So this will be error free most likely. But I assume that the pulse shaping they use is the same in both cases. Right. So yeah, that's kind of a state of the art with electrical signals. What can be generated today? Right. So it's still 400 gigabit. So there, it's not really the data rate which is needed for implementing overheads, which are usually used to have when you use systems operate with forward error correction codes, then you need to use to achieve 400 gigabit net rate. You need to, depending on the forward error correction limit code, you need to use, for example, 448 gigabits per second or 224 gigabaud. So in 112 gigabaud, these 12 gigabaud are included there as an overhead. So your data rate in the end is 200 gigabits net data rate, right? So these are not standard rates which are tested, but yeah, okay. Then there was also other things which can be problems with these kind of signals. One of these potential problems which can be there uh, is that these eye openings here cannot be with equal levels. Then you kind of start to get nonlinear distribution of your four signal levels. And then if you measure the eye openings, then in this case, like here, you can already see that this eye is smaller than this one. And then you can see also here that if you do the test if you scan your threshold over here, then you can see that the eye closes not so fast on the middle, but it closes faster on the top and on bottom. So then you kind of start to get non-linear signals, and of course you want to avoid this because then you will have quite a lot of errors here. Here you have less errors here, but yeah, so then you kind of get a non-ideal distribution of levels, which will result in more errors here. Right. There's also another issue which can happen is that these levels of eye levels. So it's kind of becomes if I draw a line. Then the optimal transition, it goes like this. So the eye becomes tilted. The eye becomes tilted. And that also needs to be corrected. Otherwise, it will result in a penalty because if you sample here, then at some signal to noise ratio, you'll get things right here, but you will not get things right here. So that can be a potential problem. And here we also have another parameter which is used to quantify these pump force signals. It's called TDEC-Q, and I'll give the equation in the next slide. It's nothing to be it's not that you need to know formula by heart, but it's just to know that in pulse amplitude modulation signals, then this TDEC-Q is used as a metric to estimate, and it's related to this optical modulation amplitude, what we talked before, and then you also calculate what is the threshold here, and then you can estimate the noise, what is in there, and based on that, you take this optical modulation amplitude, and then you have you have three different thresholds which you need to take into consideration here, and it's measured in decibels, so that's why logarithm is here, right? So yeah, so then you kind of can estimate estimate the bit rate or target symbol error ratio for great coded pump force signal. So yeah, just an example, and this is how you, for example, if you measure, then you kind of look on these four levels, and then you kind of get the distribution. So this is done in this sampling instant. So you kind of get almost Gaussian. Here is a Gaussian, but here partly Gaussian signals. So that's one more point when you look at these kind of estimated estimations of signal performance, then you need to know that the statistics for each level is close to Gaussian. I'm going to talk today a little bit more about bit rate estimation from eye diagrams, and there you need to be aware if the distribution is non-Gaussian, then maybe you don't have the good estimation of bit rate there. Right. So then this is just another example of these kind of impairments. So what can you do about it? Of course, you can do things with the test and measurement equipment, and also you can try to do something with the digital signal processing. So yeah, just these two examples again, and this is a typical digital signal processing routines we are using in our experimentation. And we start with, so there are two, so here's quite many things on this slide. So I wanted to talk separate. So we have two things separated here. One is transmitter part, other is a receiver part. And then you kind of have DSP routines for each of these parts. So this is an example which we use in our experimentation in the lab when we perform research. So what we do, we first generate some random bits, and there we use this generator. So I don't go too much in details here, but just to give an idea that digital signal processing can be used both on the transmitter side and on the receiver side. So, and depending what you use on the transmitter, then you need to use similar processing on the receiver side, which goes, for example, for these pulse shaping filters. So you want to match these pulse shaping filters, transmitter and receiver. But the problem is that if you have a bandwidth limitation in this green line here, then you cannot get the match filter ideally, because the pulse shape of the signal which comes in is different. And that's why you need to use this equalization in the system. I will go into some details later today about specific parts of these with specific parts of each different blocks. But I mean, the basic idea in the transmitter side that we generate bits, then we convert them to symbols, usually using gray coding. Then there's some operations we need to do. So we need to give, yeah, in this case, when you have zeros and ones, we need to convert it to samples. So we kind of upsample the signal. So for each symbol, then we have 4 samples. So it's kind of we have a yeah, and then we can perform pulse shaping to get on also analog signal. Yeah, so this happens later on in the instrument, but you do a pulse shaping to shape the signal, and I'm gonna talk a little bit later about what pulse shaping is and how does it look, especially in this case. And since you upsampled it for 4 samples per symbol, then depending on the symbol rate, for example, if you have a 100 gigabaud signal, then we have quite a lot of samples. But then these samples might not match with the instrument, and yeah, it's a bit of yeah, it's a small detail, but yeah, that's the block which is needed to adjust the sampling rates of these signals. Then in the receiver, you kind of apply again a match filter, which is matched to the shape. Then you upsample again because you need quite a lot of samples to do, for example, clock recovery. So you need to know where so 2 things happen. So 2 things you need to know, because this part here and this part here is usually not synchronized. So then you need to go through all the samples you get here. So here it's just the digital signal processing routines, but this is one instrument and this is a second instrument. This instrument is called arbitrary waveform generator. This instrument called digital storage oscilloscope. So what you can do with this digital storage oscilloscope is that you can record electrical signals of a certain duration, and then you record the samples of these signals. And what you need to do is to, when you receive samples, and then the sampling rate of arbitrary waveform generator and digital oscilloscope is usually the same. In this case, AWG can also be regarded to digital to analog converter. And on this side, we have analog to digital converter, so to get back digital signal. So in the middle, we kind of have analog signals which are transmitted over optoelectronics. Right. I think we take a short break, and then I will talk a little bit more about different other parts. So why do we need a decision feedback equalizer? What is equalizer as such? And then we can perform usually a bit rate counting. We compare bits, what we have, these bits, we compare random generated bits with the bits we receive, and then we say, okay, that's why also you need to have a clock recovery. So you need to know which bit to compare to which bit. Right. Okay, but then let's take a 5 minutes break, and then we be after break back.
Recording stopped. Recording in progress.
So hello students, are you back? Can we continue?
Yep.
So then, as I said, that there are some certain things you do at the transmitter side when you do digital signal processing, and then you do also some things on the receiver side. And these blocks here can be very different. I mean, if you're gonna look in some literature, then there are different methods how to, for example, perform a clock recovery or how you do equalization. So in this case, it's a decision feedback equalizer. I'm gonna talk a little bit more about that. But this is what we kind of use for multi-level signals for pump signals. So I have a bit of some more slides on pump signals more, and just to look into how we design those. So I think we already covered this one. So here it can be different types. So we're gonna look on digital pulse amplitude modulation, and then that we have a constrained alphabets, and yeah, so this specific alphabet at the transmitter, it's meant what types of bits we kind of put through the system, and then it's a different representation of what I showed up there. So it just that you generate pulses, then you have a filter for the transmitter, then you have a channel, you add noise, and then you have a receiver filter, and then you kind of do symbols when you recover the clock. So right, and I don't go too much deep into equations, right? But then there's this one that here we look at two-level signals. This is why it talks that each symbol takes two levels, so A1, A2, so 0 level 1 or level 0, and in multi-level then you can have 4 levels, 6, 8 levels, and then signaling period, it's related to symbol rate, or it's also inversion proportional to the bandwidth of the system, and then you can describe how you can write these signals in time domain, and then or yeah, so then you kind of can define that there's this pulse shape, and let's look a bit more in that pulse shape more in the lecture. So so to generate this pump output signal, so we kind of yeah, we kind of can choose what type of transmitter filter or pulse shape can be, and this is like it's combined from a weight impulse function, so functions. So that's so eventually each of these pulses, each of these filters has their own required shape. So let's look a bit more about visualization. So for example, if you have digital signals going through the filter, then you kind of get like analog signal, you get the pulses. I think here you also need a bit more than one pulse to get these type of shape of signal, just for a visualization of what you do when you filter the impulse train with the transmitter filter. So this is how it looks like, and then yeah, so that's one way how you could do this, but then yeah, then eventually your all responses depending on each pulse response. So and then in the receiver you get this, so yeah, so then you can detect the data with this With the slicer, you can decide whether it was level 1 or level 0 which arrived. Right, and then you need also to sample the signal on the right optimum instant, and then you can kind of sample this at the when the pulse magnitude is the highest, and then the noise and time delay. I mean, you need to know what is the time delay required for this optimum sampling. And in this optimum sampling, then you kind of get the widest opening of an eye diagram, and yeah, and then you can decide with the threshold where this is. So here is just a visualization of that you have a transmitter data, then you have a symbol. Here we have two symbols, plus A, minus A in this representation. Then here is a impulse duration, or which is related to the symbol rate or bandwidth of the symbol. And then you can have plus A, and minus A. So you have positive or negative pulses. And then you need to use the sample clock, which needs to be here, not here. So this is where you have the highest amplitude here. And then when you sample the signal, then you get the digital signals up, down. So and then you can detect 1, 0, 0, 1, 0. So you can get back that with the slicer. Right. So then the important thing is that in these systems where you use no digital signal processing, that you need to have very good clock signal. Either you need to deliver it there by clock distribution, so then you know at which instant to sample. And when you use, for example, instruments like pulse pattern generator or an error analyzer, then you need to know and you need to distribute this clock quite efficiently. And yeah, and if you use, for example, instruments like arbitrary wavefront generator and digital storage oscilloscope, ADC and DAC, you not always can do clock distribution. So sometimes you need to do a clock recovery from the received signal. So that is the problem in practical systems, that you need to recover it from received signal. Then so here we talk about little bit about coding, and when we kind of look in different different patterns of bits. So we're gonna talk about that a little later. So right, but then you need to also know what type of pattern you have to perform synchronization. So that's important to know where your pattern starts and where your pattern ends. So that's needed. Okay. So what happens when you have this coding? Then you need to increase the symbol rate. So and these coding schemes, they help to avoid errors. So you can correct for errors when you use them. But okay, and then also if you do if you apply specific filter here, then you can extract also other spectral components which can help to get this clock signal generated. And then you need to do a different processing to get this clock component out of the signal, right? So, and that depends on what type of signaling like coding or bits and zeros you use there as for, yeah. Right, and one thing there is that which makes it harder to happen is this intersymbol interference when you're so this is told in time domain, but if you look at in frequency domain, then you kind of have an impulse response, then if this bit is extended, this impulse response gets wider, then you kind of have a problem with intersymbol interference. Right. So if we look here on when you don't have intersymbol interference, or when you have intersymbol interference, so your symbol would look square, and then it stays within its duration from 0 to 1. But if, for example, we have RC first order the response of the system, then you kind of have a impulse shape changes, and then you kind of get a tail which impacts the following symbols. First, of course, you get delay in your signal, and then of course you get a tail. And so then the problem is that you cannot close these bits quite close to each other, one after another, or yeah, so that is problematic. Right, here is a good representation of it. When you put zeros and ones, and then it's difficult to decide that at the middle of a pulse whether this is 0 or 1. It's really on a crossing, so it can be 0, it can be 1, but you detect it as 1, and here you detect it as 0. So then you kind of start to get superposition of these individual pulses, and that is the impact of intersymbol interference here. And yeah, so what you can do, then of course, yeah, I think here is also a bit about how it impacts where you have this timing recovery, timing instance, where you have them, and how can you decide that, right? Okay, so here is another representation of this, that you get a received signal, and then you kind of get individual pulses for ones and zeros. So it's just a MATLAB generated plot. When you have a superposition of a pulses, what happens when you have these intersymbol interference and pulses are close to each other, and how they look like as a received pulses, and what are the individual pulses which contributed to this received signal, right? Okay. Then if you have this system with yeah, if you have a longer sequence, so then you have received this one, and then you can decide it, and this is how the longer sequence looks like, and these are the individual pulses which are there. So yeah, so this intersymbol interference will cause quite a lot of errors when you try to make a hard decision, whether it's 0 or 1, especially when you have a different patterns. So we have different types of errors in the system. Okay, so then here's a little bit, we already covered about eye diagrams, and we already know that we kind of overlay all the symbols in the system on top of each other. So so then you kind of see that yeah, so with eye diagrams you can do several things. You can really look at intersymbol interference, about noise impact here, and yeah, so you need to have oscilloscope which has a clock signal to it, so you can visualize it, or you need to do this signal recovery in digital signal processing model. So when you have a digital signal, when you work with it. So here is a typical eye diagram when you represent overlay all these pulses, and depending on what type of so I think that this one is important. So depending on a pattern you have here, depending when you have several ones and several zeros, or several ones and just few zeros, then you will have a double trace here, depending on your bit, say the random bit sequence. For example, PRBS7 here. Yeah, so you could have double trace here as well, which indicates that there's quite significant bandwidth limitation in the system. Right, and this would be like optimum sampling instant where you need to sample the signal. And this is just an example of RC response. It's not a particular communication system. Right. So the eye height, it's like whether we're gonna make decision correctly, because that is how wide open the eye is, and how far is 0, 1, so level 1 from level 0. And so then the maximum opening occurs at this optimum sampling instant, right? And then if we look in the width of this eye diagram, then it shows what resilience it has to different symbol timing errors. Yeah, so and then in multi-level signals, then you have more eyes than one. Okay, so right. So here is just some examples, right? And then that you usually use random data symbols. So what you here we come to pulse shaping, and this is a way how to avoid intersymbol interference, and then you can try to use you can really satisfy this Nyquist pulse shaping criterion, so you don't really get long tails of pulses. And yeah, so here is a proof that this intersymbol interference can be avoided, but we need to satisfy a specific condition. Right. Okay. So then let's look. Visualization is always the best. So if we have pulses like this, then you kind of yeah, there's still overlay here, which is not really good and not what we would like to do in a frequency domain. So yeah, so here is just an example, and then what you could do here is to apply Nyquist pulse shaping to constrain your symbols, your symbol bandwidth in specific place. So and that is called a Nyquist pulse shape, where we have a where we can define it in this way. So the problem with this Nyquist pulse shaping is it's really hard to design these practical brick wall filters to get this very bandwidth limited and time limited signals. So yeah, so and then the problem is that yeah, so right. Then we come to raised cosine pulse shaping, which is done in this way. I think we need to look at the visualization to understand this one better. So here is response, and we can look in three different parts. So for this part, which is up to here, then this part is this shape, and this part we would which when it's larger for this one, then we assume it's 0. So we have these kind of so So we try to optimize this one in frequency domain, right? And then you can get also corresponding time domain impulse response. And so the thing is that if you try to optimize this beta, then you can do a trade-off between the bandwidth and pulse decay rate. And then you can normalize it. But what happens if you try to do so? For example, if you have a beta with 0, the spectrum of the filter is rectangular, and time domain response is sync pulse. That looks like this, and the time domain pulses have 0 crossing at intervals of this of desired on desired value. So we're gonna look at it. But if, for example, if this beta is a value, then we kind of have the pulse with the low side lobes. So we're gonna look at the visualization. It's easier to look here. So so we have on one side we have a frequency domain. On this side we have a time domain. So we have a square spectrum, and then we have sync pulse here. And then if we try to shape this one, then we kind of get pulse like this here. And if we put shape like this, then we have a pulse like this. So so these sharp so these sharp frequency domain, this is what you would like to do in frequency domain. So you don't have large tails of these signals, but then you kind of have these ones in going into the neighboring bits pulse shapes. So you need to optimize this one and this one, right? So yeah, and this optimization you do based on what type of signal bandwidth, or so system bandwidth, what is available. So then you do this type of pulse shaping on the signal. Right. Then if we go further, how the eye diagram will look like. So here, for example, if the beta is 0, so it's very strong pulse shaping, then you will have a wide opening here, but you have a lot of transitions coming up and down. And in this case, so this pulse shaping is this pulse shaping is used when you have a limited system bandwidth, but then you are more tolerant to timing errors here. And then, for example, if your beta is used like 1/2 of a symbol period, then you kind of get this shape and this eye diagram opening. So these are two very different cases. So amplitude here is also higher, and you can see that the system has more bandwidth to accommodate this type of pulse shape. Okay. So the critical, of course, you can do this, and this is what is done in practical systems, that you get this pulse shaping and in limited systems, but the problem is that the timing recovery is critical. That this is what is the penalty as well. So you can have a inaccurate sample clock timing. Okay, so let's talk about what do I mean by that. Yeah, so then we kind of look another parameter which is called jittering, and so we look on the transition part. It gets broader. So your clock in the system is not very accurate. So you kind of start to get the value of clock which is acceptable. So you kind of start to measure a jitter, and you look at the statistics of a signal. So for example, this is jitter-free case, and then you have a jitter where you have example 1 here, jitter example 2 here. So these are then this optimum sampling instant due to jitter can shift to the left and right, and it can potentially lead to more errors in the system. I think here is a very good impact of how the jitter impacts different systems. And yeah, so what you have, so here you have a time domain I diagrams, then you have a frequency domain spectrum. So you have a non-return to zero. That's also a pulse shape. When you have a spectrum like this, then you have a very clean I diagram. So then you need all this spectrum from -2 to +2 to represent this time domain signal. Then what happens here is that you kind of can compress all of the signal into domain from -1 to +1, and that's a significant improvement what pulse shape is giving in these systems. So yeah, and that's the benefit, because then you can squeeze in more signal in a smaller bandwidth. And yeah, that is also helpful in addition to multi-level signals. But then this jitter impact on multi-level signals with pulse shaping is even more. So having very good timing recovery is a critical point. Okay, so and this is how it looks with the roll-off factor of this beta 0.01. And this is roll-off factor 1.0. And you can play with this in your simulation in Python. You can look at different pulse shaping factors as well there. And then you can squeeze the signal even more with this roll-off factor. So depending so from this case to this case, depending on a system bandwidth, you can optimize the pulse shape of a signal. So, and if you use this pulse shape in the transmitter, you have to use the same pulse shape in the receiver. And if you have a bandwidth limitation in a channel, then you need to look into another impact. So for example, here is some example from one person PhD thesis, which were defended in Canada. So it was a very good example. So I decided also to show it to you. So these pulses are, if you send it over time over the system. So this is at the transmitter, this is at the receiver. So the top case is when you don't have a channel response, which is frequency dependent. So you get a flat. So we are looking only on the amplitude response. We don't look in a phase response yet. So right. And then, for example, if you have this bandwidth limitation like here, when your channel after a certain frequency it starts to just decay like this, then you will start to look. Then you will start to get pulses which has a precursor, postcursor. So this is kind of important when we look in equalization. So there are different things what you can do when you kind of define a cursor here, which is the highest value, and they have precursor, postcursor. So this is the things we need to kind of keep in mind when we're gonna look into and compare different equalization techniques and what they are doing to the system. So basically in practical systems we always have a bandwidth limitation, or due to large amount of data needs to be transmitted, we are forced as communication engineers to work with bandwidth limited systems. So because we want to get the highest highest data transmission with a specific system, then we will always be in a condition that the system bandwidth is limited. Right. Okay. So then what you do what you do in this case, as I said, if you have bandwidth limitation, then you can use this magic box that's called as an equalizer. So what you do with the equalizer? You try to make the channel flatter. So, and then ideally you want to make it completely flat, but it's not possible because here this is just an ideal picture. So, and this equalizer can be done at the signal either on the transmitter side or on the receiver side. So here we have a definition of pre-equalizer and then post-equalizer. And then these two equalizers can have very different parameters, and depending on what is the linearity in the system, or what is, for example, not only linearity but signal to noise ratio in a system, or if I can say simpler, what is the voltage swing available at the transmitter, then you can decide, okay, how strong equalizer I will use in a transmitter, and how strong equalizer I'm going to use in the receiver. And these are the things we need to optimize all the time to achieve the highest bit rate possible. So I'll just show just some of the example what happens again if you have a pre-cursor, post-cursor. So this is in time domain, single pulse, and this is in a frequency domain. So basically your frequency response starts to decay faster and faster. And there are different parts in this optical communication system which will create this type of effect. So you can have this decay due to transmitter components, you can have it due to receiver components, and intensity modulation direct detection systems, you can have this kind of effect also at a specific wavelength, which is like C-band 1550 nanometers, where the dispersion is 16 picosecond per nanometer per kilometer, and then you use a square law detector. Then you kind of start to get the bandwidth can get smaller depending on the how long the fiber is, or how much dispersion is there in a system. So right, so that's another effect which limits the choice of wavelength for these transmitters, and also so also choice of equalization, what you can do. So what is equalizer? So here's a visualization of feed-forward equalizer, which we have on the left side we have an eye diagram. And what happens when we apply equalizer is that the eye diagram becomes cleaner, but there's one more effect you need to consider. So it's not only that you gain things when you use digital signal processing. For example, this one is a feed-forward equalization. I will show the structure, how it is done. Then the thing is, when you equalize the signal, then you lose also modulation swing, or electrical signal amplitude in the receiver decreases. So that happens there, and then you can see, but then what you gain, you lose something, but you gain something. You gain that your eye opening here, before after channel you have like this, but then if you apply feed-forward equalizer, then your eye opening can become like this. So you can really open eye diagram by using this equalization. Right. So what's happening there is that why it's called feed-forward equalizer, because you take a sample, you kind of you need to kind of create this you need to change this shape of this decay here. You need to decrease it, so you need to make sure that your impulse response stops here. So then you kind of apply compensating signal just to compensate out this part. So we can look a little bit more here. So what you do, so basically you have this pulse, which is purple, or slightly rows. So and then you kind of have a then you can kind of define that at this highest level you have a cursor, so you have a precursors and you have a postcursors, and then what you need to do, you need to generate a pulse which has this kind of shape. So just to cancel out this tail and cancel out this tail. So just to confine the signal energy here. So that's how you, that is how it is done with this equalizer. And then what happens is single pulse after feed forward equalizer that you get from the to the blue curve, where you have a bit of negative coming down, but the amplitude also is decreased. But then the next pulse, you basically you don't have this tail, positive tail, so it's bit negative on there. So that's why in this way this feed forward equalizer reduces this inter-symbol interference. How do you generate these types of pulses? So you have a one pulse, then you do here is very important. So here we can see 4 different tabs. So we have cursors. They're also being called tabs, and you can so this feed forward equalizer, it has an identical it is identical to finite impulse response filter. So you kind of get your signal goes through delay, depending on this coefficient, negative or positive, you can get changes in your signal. So these are the coefficients which are defining and the taps of a filter. And then you have a delay, which is you can have a symbol spaced equalizer or half symbol spaced equalizer. So this delay can be optimized, and these coefficients can be optimized to sum up and to get this one signal here. So the really so the real difficulty in these type of filters is to optimize these coefficients. So let's look another example here. Again, these so I already told you a little bit. So C0, which is cursor tap, then you kind of have the largest magnitude. So this is your C0, and then you have a -1, and then yeah. So here how you define which whether you look in precursor, postcursor, and then I mean the biggest problem usually is with the postcursor, and then this number of these tabs in time domain. These postcursors, number of those just requires how many tabs you need to get rid of this tail. Right. So and then also there's some examples about how this also losses impact the inter-symbol interference pre and post cursor. So I think the critical part here is to optimize these taps, so or these cursors. How do you set those? And that needs to be that can be used with different methods. So here is one example. So this least mean square and recursive least square algorithms. So yeah, so and this is usually optimized. Then there's also another equalizer which works also with the way of feedback. Right. So and then you kind of get a different type of signal, but you also get a bit of distortion. But still, you can open the eye diagram, and this is also showed how many tabs you have, just to get it more clean. So here you basically you take a copy of a signal and you delay it and you sum it back. So in this system. So if we look here, so then single pulse after DFE is this blue one here. So you kind of have a lot of focus on a post cursor. And so DFE really corrects only post cursor intersymbol interference. Right. So you kind of get this is what you see on eye diagram. This transition here you saw in that example, and so and this is an example of if you transmit 1, and the next is 0, and if you transmit 0 and the next is 1. So these are the transitions you see in the eye diagram, and this is how it looks like if you have several pulses, like different bits coming one after another. So you can see these excursions here. But yeah, so this how it looks like when you apply DFE with different number of taps. Right. So then the thing is that the DFE needs to detect what type of symbol was there if we talk about different levels. So the problem here is that so the scale is not linear. So the decision feedback equalizer is a nonlinear equalizer. And yeah, I think I'm already running over time, but I still have the short. So yeah, you kind of have a feedback filter, symbol detection, then you have a feedback filter, and then you can have also feed forward filter. So that's a typical. So you have two parts. You have a feed forward equalizer, and you have decision feedback equalizer. So this can be used together, and that's how we usually use the DFE. And here just a comparison between these feed forward equalizer and decision feedback equalization that you get. It's a linear, it's a time domain digital. Then you do pre and post cursor, and on decision feedback you can do only post cursor. Then you need this feed forward part there as well. But this one becomes nonlinear. But yeah, so then there's a number of other things about the bit rate estimation, but I think that we're gonna take in the next lecture. So I'm gonna stop recording.
Recording stopped.
Okay, so I think now I can give a floor to Daria if she has something to remind you. I think it's important that you really focus on practical works and course assignments, but I give the floor to Daria so she can remind you.
Thank you. Thank you, Oskar, for the lecture, and hello there, students. I will just quickly remind you and as well show my screen. And so that you, the last week, I started the second practical work. So you should be already working on it. I hope so. So just to remind you, here in Ortus, you have practical work number 2. As well, this week I added practical work number 3 and 4 that will be issued later. So if you already finished with the second one, you can move on to the third and fourth. Of course, you should read the chapters in corresponding chapters in the book as well. I hope so. Then please do not forget about your coursework. Slowly but surely you can already start the coursework, because the coursework mainly, if you look through, I hope you already looked through the second chapter of the book. It has already some tasks to finish in MATLAB, and these tasks are included in your coursework. So you are definitely are encouraged to start working on your coursework as well in parallel with your practical works, of course. So the second practical work, I have it already opened here. So you have as well some more like theoretical questions to solve. And as well, you have simulations to finish. It would be mostly about intensity modulation direct detection that were already mentioned during the lectures. And here as well, you will look through different modulation formats on of King, PAM4, and PAM6. So now I think we should just open the simulations in Python. So this is the link. I've already opened it, of course. Quick reminder, you have here the book, the link to the documentation, which could help you to finish your practical works. You can search for the functions and read more about them, understand what they are doing and how to finish your tasks. And then for your second practical work, we'll go to examples again as always. And then we have here basic IMDD PAM transmission. This is the one example we are looking for. Of course, you should open it in Colab. I have already opened it here, and we will just briefly go through. Maybe I'll catch some parameters that you are encouraged to change in this practical work. I will just move that description to that screen. Hopefully, okay. So I can see which parts to. First of all, you should notice that this code in Python is made of the different parts, I would say. So the first part is just simulating one case of the IMDD transmission. So here again, you have some parameters you're encouraged to change. For example, here you have the order of the modulation format. For now, is set to 4, so it means it's PAM4 on the default. To set to on of King, you should change the level form this level to 2, and to get PAM6, to then change it to 6. Here you can change the symbol rate as well. And here, if you notice, maybe in the previous code, in these simulations, we usually have the pulse shaping as well. So this is one detail that was as well explained to you during this lecture. And here as well, we have the spectra of the RF and optical signals, and how our binary data is looking. So you can see here it has this four levels, so it's PAM4. So yeah. And then we have some amplification parameters for our optical channel, and then we have our receiver. And here we can see how our eye diagrams are looking, and from the transmitter and after we received it. So you can see some of the distortions a little bit that were mentioned during the lecture today. And as well, there are some parameters you are able to change in all of this part. But please notice, if you are going further to the BR course, then you should change the parameters here separately. So in the end of the code, of course, you get the result of the number of the BR. So it basically shows how many bits were detected incorrectly compared to the all bits you transmitted. So, and there are two parts which generate BR cores. This part generated versus the received power. If you want to change some parameters, your work as well requires to record how this graph would change, then you should change the parameters within this part of the code. And then as well, you have the code part, which is bit rate versus transmission distance. So here you can see the curve which is generated, so you can see how the number of correctly received bits or incrementally reduced bits increase if we increase the distance. So no, these simulations could take some time because it uses the code uses the estimation, which takes some time to make the calculations. So the results wouldn't pop instantly. If you are really interested, you can dive deeper in the code and see how this modulation is made in this Python code. So I hope this helps you with your practical work. I hope you already submitted the first practical work report. And in case you have any questions, you can ask the questions now or write me an email and hopefully I will be back with the answer soon. Okay, you have any questions?
I have a question. In all of these simulations, the electrical signal part is called the RF, the graph. Why is it called the radio signal? Why not electrical? I was just confused about why it's called that.
Sorry, maybe I can explain. This is radio frequency signal. So I mean, these electrical signals quite widely have been used first in radio. So I think it just and then the person who wrote this code, I guess he used it from that purpose, just to differentiate. Whereas optical signal, where you have a higher frequencies, and where you have electrical signal. So this one could correctly be called electrical signal spectrum. So it just a choice of an author. So this is my collaborator from Brazil, and he has developed this signal processing routines and then the simulation software. I think this was during the corona pandemic times when he had time to devote and to give a possibility to do remote simulations with this Colab in environment. So this is just a naming. I mean, yeah. So you can call it also electrical signal. So I think that's just to differentiate between optical and radio signal, because the frequency is much larger. So this also RF signal can also be called a baseband signal, and then that can be also optical signal spectrum. Then you have modulated signal. So these electrical signals you have in before modulator. So and then when you up convert this baseband signal to modulation, then you kind of get this optical spectrum at a carrier frequency. If you go slightly lower, then the students will be able to see that here it's also normalized to zero. But what is in practice, so this is normalized to zero just because of a simplicity for simulations. In practice, this would be from 0 to some gigahertz. So you have a double sideband spectrum, and then this frequency here lower on optical spectrum, it will not be 0. It will be a laser frequency which you use for a light source. So it will be like 193 terahertz, for example, if we look at the C-band transmission. And then he just want to show that after putting on a modulator, this electrical signal has the same shape, but it has a carrier here at 0 frequency. So that's our carrier frequency, our tone, around which we have the modulated signal. So I hope this clarifies.
Yeah, thank you. It just confused me slightly because there was no indication of it being a radio transmission before, so confused. So yeah, thanks.
As well, I looked up the definition, what is the radio frequency, and basically it's the oscillation rate of alternating electronic current or voltage or magnetic, electric, and so on in range of frequency from 20 kilohertz to around 300 gigahertz. So it's just to simplify the name of the signal to give the students who would be interacting with the code that this signal isn't like in some kind of DC power or something like this, but it has some frequency in it because we have this frequency in which we change the amplitude that we have our bit rate and so baud rate as well. Yeah. Okay. Any other questions?
Can it do coursework individually?
Yes, you are allowed to do the coursework individually if you wish. You just pretty big amount of the tasks to finish, so it would be just a bit simpler if you have a partner to finish it with.
Okay, thank you.
But you are allowed to. That's no problem. We're just encouraged to work in teams of two. It would then be a bit easier for you to finish the amount of the task and great to work in a team. It's great for you to learn how to work in a team.
I think if you are individualist, we don't mind that you do it on your own, because people are different, so you have different.
Of course.
I think it's
course.
one skill you can learn. You can also learn from each other. I think, and the amount of work in these courseworks are made for two persons. So I take that into consideration.
Yeah, I received a question in chat. The members in a team could be only 2 people. So you can work in pairs. No
Okay.
more than 2.
Yeah, okay.
Yeah. Okay. Any other questions? Guess I will. Yes, if there are no questions, then we can wrap up. And thank you for attendance and see you next week.
Yeah, thank you for today. Daria is gonna inform you about
Thank
the
you.
next event. So yeah, I still stay, but you are free to leave. just in case someone wants to talk something a bit more. So thank you for today.